Okay, good morning. Good morning. This is the last day of EuroPython in Florence. I'm so sad, but here we have Joe Gordon. If you are interested in OpenStack and how to manage a very large-scale project, he has the answers. Thank you, Joe.
Thank you, and good morning. Today we're going to talk about very large development, how to run code review for a big, large Python project. So about me, I'm an OpenStack developer at HP. I've been working at OpenStack for about 2 years now, and HP for about a month, so still pretty new there. So very large development, what is it? So all numbers here in this presentation are from olo.net. So olo defines very large as, in this case, it's recent development, and so it's 889 developers in the last 1 year. And OpenStack is in the top 2% of all projects on olo, and one of the biggest ones in the world. So what is OpenStack? It's Python, lots and lots of Python. It's 628,000 lines of Python, plus comments and white space and other files as well. So it's massive, and there's very few projects on the scale of OpenStack and Python. I've been trying to find answers for that, what's bigger, and it's been hard to find those numbers. But the only project I know of that's bigger is PyPy, at just under 1 million lines of Python itself, no comments, no spaces. And if anybody knows anything bigger than this, I'd be happy to update the slides and find out about it. But there's very, very few projects that have been working on the scale of Python, a scripted language, and massive, massive, massive scale. So OpenStack, as some of you may know by now, since we have a bunch of people here and a bunch of companies and a bunch of presentations, is APIs to programmatically consume, allocate and consume compute, network, and storage resources. And so this is the simplified PR diagram we have for what OpenStack does and what it looks like. This is what it looks like to a user. You want to spin up an instance, you want to spin up some networking or some storage. This is what it looks like to you. Underneath, it's a bit more complex than that. There's a lot more than just 4 different pieces here: a dashboard, compute, network, and storage. There's a lot more underneath all of it. So this is from a more developer point of view, what it looks like. This is the different services. We have a dashboard. That's a big Django app we have. We have networking, which just recently changed from Quantum to Neutron because of copyright infringement. So we're going through some growth pains here. We have block storage, compute, image, object storage, and an identity service to manage identity across all these services. And then we have many, many more services that are coming online as new incubated projects will be out in the next 6 months, year and a half or so. And so that's still a simplified diagram, and this is what it actually looks like underneath. So it's even bigger than that. Each project itself, for example, compute here, has a whole bunch of different components to it. And so each one is running many, many services across many, many machines. So this is a big, complicated piece of software that runs on many machines, a lot of moving parts, a lot of different projects we're working, trying to coordinate together. And it's just a big mess, as you can see by all the messy lines on this diagram. So who is OpenStack? So these are the top. OpenStack is run by a foundation now, similar to other big projects, Linux, a whole bunch of others. And these are the top 2 tiers of members to the boards. We have some big companies here: HP, my company, AT&T, IBM, Ubuntu, Red Hat, SUSE, Cisco, Dell, Intel, and many, many more. And then those are just the people who are on the foundation. And there's a whole bunch more people actually using OpenStack in production today: PayPal, Cisco, CERN. There's been a bunch of news about CERN using this. NSA, which we're not necessarily happy about anymore that they're using it, but they're using it for something. We're not really sure what. Canonical, KT, DreamHost, some big clouds on it now. A whole bunch of big companies have been putting lots of work in using OpenStack. So it's starting to gain momentum, and you're starting to see it in the marketplace. So unfortunately, this is cropped. The bottom here is cropped, but this is a rack-based data center. So deployment scale, what are we trying to do for an OpenStack? What scale are we trying to aim for? Aiming for the data center. So this is actually, you can see if you look carefully, this is actually an empty data center, unfortunately. But this is one of Rackspace's data centers that are deploying an OpenStack cloud into. So we're looking for the whole data center. We're not looking for small scale. Everything's big here. Things where OpenStack works on small scale, but we're trying to make it work on a large scale and data center scale as well. So we're trying to make this big, complex system work on this big, complex scale. Not only is we're designing this thing for a big scale, it's being developed on a large scale. And so that makes things even harder. So everything about OpenStack is big. So trying to work on the biggest deployment I know of is 16,000 nodes. So one cluster, 16,000 nodes. There's a whole bunch more clusters of similar size out there. And we're trying to develop this with 900 developers over all the time zones that I know of. So by the numbers, the last 30 days, this is also from Olo, there's been 2,200 commits over from 290 contributors. Last 12 months, it's been 24,000 commits and just under 900 committers. So that's a huge scale. There's very few projects in Python that work at this scale. Things like the Linux kernel are massively bigger than this. We don't even compare. I think they're like one or two orders of magnitude bigger than us. We've been around for 3 years. They've been around for a few more. So the past 3 years of OpenStack, and it's turning 3, I think, next month, next week maybe, actually. There's been just over 1,000 contributors, and there's been 65,000 commits. So this is a lot of code, and a lot of it's moving quickly, and it's been growing by leaps and bounds. So this is a graph over time. Unfortunately, this is cropped a little bit. Sorry about that. In January 2011, this is early on in the project. That was into the first year. There was only 61 contributors and 71,000 lines of code. And now we're just under 600,000 lines of code. So we've grown by an order of magnitude in 2.5 years or so. So this has been a huge accomplishment for us to be able to grow at this scale and try to maintain, improve the quality of the software and improve the numbers, grow the number of services we provide, and to make everything work at large scale. So this has been a big challenge for us, and we're pretty proud of the results we have. So as some of you know, and hopefully many of you know, Python's a great language. We all love it. But there's some pros and cons for using it at massive, massive, massive scale. Pros is fast to develop. It's fun. Hopefully everybody here agrees with that one. It's a very approachable language. That's one of the reasons we've been able to grow the project so quickly. It's very easy to get, say, hey, start working on Python. It's easy. A lot of people already know it. If they don't know it, it's not too hard to learn. And that's one of the ways we've actually been able to grow the project to the scale it is today. And without that, if it was something like C, we would not have the success we've had today in this. Some of the cons is that it doesn't really work well at large scale. It's not designed for, doesn't have really good type checking, if at all. There's been good talks here about how to do type checking in Python, but they all involve adding more data into the system, doc strings or whatever it is. Other static analysis isn't as good as it could be for a compiled language, I'd say, and it doesn't have really built-in concurrency. That's something we want to use in a large system. Even small systems still want to use concurrency, and that's been a problem for us, although we've been using Eventlet for that. It's worked very well for us. We've hit a few snags along the way with Eventlet and filed bugs upstream and are working through those problems with concurrency. So these are some of the problems that we've had to try to address in making the development process work for Python and large scale. So the development process itself. So a very common way to do development today is on GitHub. It's a great tool, and we all love and use it. And it's great for really small projects. And this is the sort of standard process on a small GitHub project you're running with some friends or in a small company. You fork the repo, you go to, it's running from, for example, pep8. Let's say pep8's on there. The guy is not in the room today, but you fork pep8, you make a change, you write the code, run the test, you push it up to GitHub. Then you say you submit a pull request. The patches are viewed by the maintainers or anybody else, and then you fix the patch up as you go along to amend, fix any negative comments, and the code is merged, and then something like a Travis CI runs on trunk to see if it's green or red. And this is example I took this morning, and that little, I'm sure all you've seen that little icon, build is green, build is failing. And it's very useful, but this didn't work for us, and so we've had to evolve our process. So where we started actually on Bazaar and Launchpad, so no Git. This was 3 years ago. GitHub wasn't really the powerhouse it is today. It wasn't as feature rich as we would have needed it. We used a tool at the time, which was Launchpad and Bazaar. This is an example of an early patch. It's very similar to the process, but Bazaar is, bizarre in some cases. And it didn't work for us. We wanted to improve the process and make it scale a little better. So the first thing we did, so this is the evolution of how things have changed since the beginning. The first step is going to Git and Garrett. We all love Git, hopefully, here. And I don't know, anybody here has used Garrett before? Or just Shmuel and a few others? OK. Garrett's a nice tool. It hooks into Git very well. It hooks into a common use case is Git, Garrett, and Jenkins. They all work very well together. And it's a nice review tool. So it's designed for reviewing. You go on there, you push a patch up. Somebody provides feedback, inline comments like this one. You put comments at the bottom. You could amend your patch, have histories, and it manages the merge process. And it's a very nice tool for just doing high-quality reviews. One of the nice things actually is the inline commenting. It's a really great feature. We all been really enjoyed it a lot. This is an example of early on what things look like. So everything was manual. We just had Git and Garrett, so we could do inline commenting. You could amend a patch. You could have a whole discussion at the bottom, things like that. But unit tests were run manually. So this is an example of a guy saying, I tried running this, it didn't work, something's wrong. So this was nice. We could actually do this now, but this wasn't really enough. This is sort of a slow process, and nobody really wants to run the unit test, which could take a long time. OpenStack now, the biggest project, Nova, has just under 70,000 unit tests. So we have a lot of unit tests. They take a long time. With all the improvements we have now, I think it's about 5 to 10 minutes, depending on your computer. So even that's pretty slow. So we don't want to actually have to manually run this all the time. And when you're doing this manually, just like this, trunk breaks, somebody misses something, somehow it happens. We're all only human. And you have to fix trunk, and it breaks, and nobody's happy about that. When you have 800 developers, somebody wants to kill you if you break trunk. So that was the first thing we did, is we actually decided to gate on pet-bait and unit tests. So before anything was merged, we'd actually run pet-bait and the unit tests on it. And if it didn't work, then the patch won't get merged, and it has to go back to the developer to actually fix it. And so this was one of the first steps in making sure things scale, which was never break trunk. And that helped us a lot, and this is really useful for us, but it wasn't enough for us. Turns out that OpenStack, we're trying to run on many, many platforms. One of the platforms is RHEL. RHEL is a great platform, but it doesn't support Python 2.7, as many of you may know or not. So we decided we want to run Python 2.6 as well. So now we have, in addition to just running Python 2.7 unit tests, we decided to run Python 2.6 unit tests as well. We're using Tox for that. It makes it really easy to run both. But now we have twice the amount of work. And additionally, unit tests are pretty good. But for a big project like OpenStack, you want something like integration tests to really flush out all the bugs. So the next step was to start running Python 2.6, 2.7 unit tests, and then doing integration tests on every merge as well. And this caught a lot more bugs, and it made things even more stable. But we still had this problem. This is a classic review problem. You may have pet-bait mistakes won't get into trunk, but they'll get into the reviewer has to tell the developer to fix it. Otherwise, they'll try to merge it, and then you realize, oh, this didn't merge because I have a tab in there, because Python doesn't like tabs. And you have to go back and fix it. And that's a slow process, and reviewers will look out for that. And that really just wasn't a fun thing to do. You'd have to check the unit test by hand, and then you'd try to merge it. Things wouldn't merge because it broke. And it'd be this whole painful process, and there was a lot of burden on the reviewer to fix this. And reviewers are a fairly scarce resource, and we want to make things as easy as possible for them. So the next step is decided to run these same tests, the gate checks at submission time. So you push a patch to Garrett, and we'll run all the tests we have on that patch, and the reviewer could see that. So here's an example. It's similar to the one before, but this is from a patch. The guy pushes a patch. We run the unit tests on it. We run pet-bait. We run the integration tests. And he sees he messed something up on Python 2.6, so he goes and tries again. And then finally, when everything is green, a reviewer sees, oh, this patch is working. This is up to the basic standards we want. Now we'll go and actually look at the code for, does this make sense? Does this, is it done right? Does it have unit tests for it? All these other things we're looking for. And we've taken this even further. And currently we have, as you can see, a lot more tests. This was not too long ago. This is, I think, under a year ago. And this is today. Why not run more tests? One of the nice things about running OpenStack is that we have a bunch of big public cloud providers like HP, Rackspace, and others. And so we have essentially unlimited CI resources. So our Jenkins system has, do you know the number? About 100, 200, if not more, slaves to it, and we could add more. We're actually working on, Jenkins isn't scaling to the level we want it to do, so we're actually working on running multiple Jenkins with multiple Jenkins masters and pushing to multiple Jenkins masters so we can run even more tests. You can see here actually some of these tests take up to an hour, so things are a bit slow, but we have as many servers as we want. They're all VMs. We're using the cloud to develop the cloud. It all sort of works out nicely. So now we have pet-bait tests. We have doc tests. We want to make sure the docs always build. I believe that's just Sphinx. We build them all there, make sure it works. If you're changing a doc in there, you don't want to break something. I've done it many times before, and it's nice to know early on that you broke it and not have somebody yell at you later. Still run the Python 2.6, 2.7 test, and they're about, depending on the project, in this case, the Nova one, this is at 10 to 20 minutes, and it takes, it's about 60,000 tests. So it's pretty big. Then we have DevStack and Tempest, our integration environment. So Tempest is our integration test suite, and DevStack is our integration testing environment. And because OpenStack supports many, many backends, we support MySQL, SQL Alchemy, or we support SQL Alchemy, which supports MySQL, Postgres, SQLite, et cetera, we actually decided to start running the integration tests against multiple different backends. So we test multiple databases, we test 2 different networking models, and we're always looking to add more tests in different environments to support. And we also have this new tool, which, as you can see, is actually not working as of a couple days ago, which is called Grenade, which is an upgrade test. OpenStack is a big project, a lot of real case deployments. We want to make sure it upgrades, and that's been a real problem for us in the past. So we decided we're working on an upgrade test. This will take the old test, apply the new patch if there's an upgrade in it. It'll try running the database upgrade and see if everything works. But it's a work in progress right now. And we're always looking to add more tests just to make our lives easier. And lastly, we have a pilot test. This is actually an interesting one, which it's not running pilot in the whole project. It runs pilot on the year patch only. Pilot's so thorough and so detailed that making a big project, 200,000 line project, past pilot was a big project, and we wanted to get around that. And what could we do in the meantime to make sure we don't make things at least worse? And so that's where we are today. So the life of an OpenStack patch today, it's very different than the standard GitHub process. So the first few steps are similar. Code is written, you test it locally, you run Tox that runs all our tests for you. You submit the code. We have a nice tool for that, actually. One of the big changes here now is we actually have the code is tested on submission time, so not after it merges the trunk, not before it merges the trunk, but essentially every single time we could think of, we run the tests. As I said, we have so many servers we could run tests on that we just we'll run them as many times as we need to. Code is peer reviewed. The review process is open to anybody. Anybody could plus or minus your code. And then we have a set of core developers per project which have the right to approve code to be merged. And if there's any negative comments on the code, you go and you amend your patch. Eventually, hopefully your code is approved and not rejected. And then we begin the merging process. So the tests are rerun then. Just because you pass tests on submission time doesn't mean they'll pass on merge time. If your code is merged in, or maybe it's rebased depending on the situation, and something underneath may have changed that you assumed didn't change, and it'll break. An example is if somebody else touched the same line as you, you have a merge conflict. So Git stops there, and so it'll throw you an error, and Garrett will say, unable to merge, send a new patch in, or a dependency you had changed underneath you, and the unit tests all of a sudden fail. And that's something that is unavoidable right now, but that's why we rerun tests on merge time. And if everything passes, we'll actually go ahead and merge everything. So these are some lessons we've taken from the evolution of the review process. So for things we do today, some of the big principles we have is never break trunk. This was a very hard process for us to begin. As many of you probably know in your smaller projects, if you don't have any gating on trunk, it's hard to get the tests up to that working so well that you can actually run them on every commit. I worked at small companies where this has been a real challenge for us. There's not so many people, only 2 or 3 people are going to be angry at you. Maybe it's not worth it for a small scale project, but for 800 developers, you can't break trunk. In the past, it would break every maybe 1 or 2 weeks. I would see it break. Now it breaks. There are still ways of breaking trunk. A dependency changes. There's a transient race condition bug that gets in somehow. Those are really hard to gate against. Things will break and people get really angry at you, but the past year or so, I haven't seen trunk break for more than maybe a couple hours. So that's been a really great accomplishment of us. We're really proud of that. Before that, you're trying to work on something, all of a sudden a trunk breaks. You can't merge anything. You can't start new work because you don't have a clean slate to work from, and it's a whole mess, and everybody's yelling at you. And so, this has been a big help for us. Another thing we've done is transparency. Everything is out in the public. We try to keep everything open. It's an open source project. All the reviews are in public. There are private communications, emails are private, things like that, but as a principle, we try to make everything as public as possible. Automate everything. I'm lazy. I don't like doing anything if I can help it, so why not have a computer do it for you? And when you have so many patches a day and so many reviewers and so many committers, anything manual is just a huge pain in everybody. So let the computer do as much as it can for you and the least burden on the reviewer. Egalitarian, be equal. This is an open project. Anybody could go in. They find a bug, they could commit it. We try to reduce the overhead for getting involved in the project. There's not too many hurdles to get into the project. We'll review everybody equally. We try to be as open as possible. The last one is be strict, and that's to reduce the burden on reviewers. So we have a very stringent, somewhat crazy style guide, and that's because there's no right, there's no wrong style. Long as it all looks the same, everybody's happy. So it doesn't matter what you say in the long run. Whether you use PEP8 or use your own crazy thing you wrote up that's the opposite of PEP8, use tabs only. And then what matters is that all the code looks uniform, and people don't say, hey, you're missing a space over there, or I want to use that style, but you're using that style. We don't like that. So that's something the computer works really well at doing. So we want to enforce all that stuff whenever possible. And the same thing for unit tests and integration tests. We want to make sure that people always pass them, give that feedback as early as possible. We're also looking at other kinds of feedback we could give to people, maybe not gate on, but other information that's useful for a reviewer. And so we have the limited resource we actually have is reviewers as humans. That's usually the limited resource in most projects. And so we're trying to do our best to optimize the humans we have. So we have a lot of tools to get to where we are today. We have a bunch of tools for workflow, testing, integration testing, and communication. So workflow, as I said, we use Garrett and Jenkins. So Jenkins runs all our jobs for us. Garrett's the code review process. We have a nice tool to actually push code up. So if people have used Garrett in other projects, it's not so easy to actually push your code onto Garrett. There's a few commands you have to do, and it's a bit clunky. So we wrote a tool called a Git module called Git Review. And you just type in Git Review, and it'll push up your patch onto Garrett. So it makes it nice and easy. Here's a good example of it. So if somebody made a patch, he did git commit, then he types in Git Review, and it pushes it upstream. And so you can see there, new change over there. And the same thing works for amending a patch. You could use the same thing to download a patch, Git Review-D, and you pass in that number there, the 3072. On your computer, if you had this repo open, you would type in Git Review-G 3072, and it would download this patch for you to look at. So that makes it easy for a reviewer to look at the code. It makes it easy for the developer to push the code up. It's one line. It's nice and easy. It's all in hooks in the Git, so it's a nice tool for us. It makes our lives easier. This is part of the streamline everything as possible, make things as easy as possible on everybody. So testing, we use a lot of tools for testing. We use Tox. It's a great tool. We love it. We use test repository, which the command line is tester, and that's a parallel unit test running tool. So before in Nova, the biggest project, and one of the older ones, it took about 20 to 30 minutes to run all the unit tests, all 60,000 or so, 70,000 or so. That was, that's way too slow for everybody to wait. And you run the tests and you wait half an hour, you go get a drink of coffee and another drink of coffee, and they're still not done. So we have modern machines are parallel. This computer has 2 or 4 CPUs on it. Why not use all of them? So we actually had a big push for a lot of the projects to go to parallel testing. And this is available for anything that uses nose tests or unit tests. So this replaced the nose test command line. So you run tester instead, and it doesn't work well on Mac, actually, unfortunately, but it automatically will parallelize your jobs to the number of CPUs you have. On Mac, it doesn't actually have, you have to specify how many CPUs you have due to Macs being Macs. And lastly, we have as much automated code quality checks as possible. We use Flake8, Pep8, PyFlakes in our own homebrew version, which is hacking. All of these hook into Flake8, so that's the command line interface you just run. Whenever we have some sort of code quality check we want to enforce, we put it in hacking. Of late, we've been doing a lot of work in making everything run on Python 3.3. So we support 2.6.2.7, and we're looking to support 3.3 for as many projects as possible. And so that's a slow, and painful process for 600,000 lines of code. So it's been taking a while, as you'd expect, and we're doing it, step by step. So we'll make sure that we're having the right syntax for exceptions, for example, and we'll put a check in hacking to make sure that nobody adds a new exception format that doesn't look like that won't run in Python 2.6.2.7 or 3.3. And if we have we have a whole bunch of other rules in there as well to make things easy for merging and whatnot. Hacking is loosely based on, there's a Google style guide for Python that's publicly available. And one of the things they do is they have alphabetical imports, imports by blocks, and one import per line. And what that means is that it's easy to merge imports in. So you're working on file A and somebody else is working file A, and you both add the same requirement in. Merging will just seamlessly work. You'll see it's the same file, the same import in the same place, and it'll make merging much easier. You don't have 10 copies of import X in the same file. And that's made our lives a bit easier. And we have a bunch of other requirements in there as well that makes our lives easier. Some of them are in there because somebody thinks that the style should be that way, somebody else thinks it should be that way. And you say, let's just pick one, we'll put it in there, and then we don't have to ever worry about it. Never focus on it again. And so the computer will do it for you, and the human doesn't have to do it. We have a whole bunch of integration tests. We have a tool called DevStack, which is a big, ugly bash script, but it works for us. And what it is it's a big way to run all of OpenStack in an integrated environment, all on a laptop or in a VM. And it's a nice standard way of testing everything. And so it's easy to say, does this work in the integration test suite running on our integration environment? So it's a nice standard way of doing it. And we're adding support for all kinds of backends and things like that. And that's the first step for making something like OpenStack, which has, depending on how you're configuring it, 10, 20, maybe 30 services separately running. You need a nice environment to run them all. We have a tool called recheck. This is a fairly new one. We've been really proud about it. As you can see, we're actually doing a pretty bad job of keeping up with it. One of the problems with trying to gate everything is you get race conditions. We have tons of services running. We have a database in the back end, and we may or may not be using it properly all the time. We have all kinds of race conditions. So this is a way we track when we have to recheck the unit tests and the integration tests because of a bug. So we can actually see what kind of race conditions are happening the most often. And this allows us to isolate the problems and focus on them. We're actually working on setting up Logstash as well. And it's up right now, logstash.openstack.org. It's a bit slow. But that's another way for us to look at the logs and help analyze how often a race condition happens. And then lastly, we use a tool called Zool. This is something we wrote ourselves. This is because we try to gate everything on these unit tests and these integration tests we have. And some of them, as I said, take about an hour. So if you're gating everything, you have to rerun all the tests, takes an hour, and every commit, you can only commit 24 patches a day. And when you have 200 committers in the last month and 2,000 patches, that's just not an option. So we pipeline the commits. So you assume that if there's 3 commits in the pipeline, you run the unit tests on all the tests on the first run, you run them on the second one, assuming the first one will merge. And that way, if everything works out, you could run a whole bunch of tests in parallel. This is basic CPU-style pipelining. And it works great for us. And now instead of having only 24 patches per day that we can merge, there's no limit on it anymore. Lastly, communication. This is a big project. One of the problems I always have is I wake up in the morning and I live in San Francisco, and I have 50 patches to review and 20 emails because all the guys in Europe have been working hard all night or hard all day, and I wake up and there's tons to do. And so communication is a big problem in a big distributed project. And so we use some basic tools for that. We use Launchpad for bug tracking and blueprints. We actually have bug tracking blueprints hooked up into Garrett. So in your commit message, you say this fixes bug X or this fixes this implements blueprint whatever, and you can actually click on the links in Garrett and it'll show you the bug. So if somebody puts a patch up to fix something, it's very easy for you to find out what bug it was. You don't have to go open up a URL, cut and paste anything. You just click a button and you can see what bug it was. We use Etherpad for note taking. This is a big deal when we're actually in the summit. We have a biannual summit. So the next one's in Hong Kong in November. And everybody gets together and we talk about what things should look like in the future. We make plans. We put it all in Etherpad. It's a great tool for that. Day-to-day communication is done via IRC. We're all on Freenode all the time. And the mailing list. We have a few mailing lists. We have the general mailing list, one for developers, one for deployers, and a whole bunch more that I can't think of right now. So some basic communication skills. And lastly, we're always looking for more tools to make our lives easier. This is one somebody told me about a couple days ago, Clone Digger. I haven't actually looked at it yet, but it sounds interesting. Oh, there he is. Thanks for the tip. And we're always looking for more ideas. This one looks for duplicated code. This is a big problem when you have over 500,000 lines of Python, you're going to have a lot of duplicate code, and that just makes life harder. You fix bugs where the bug is in 8 places at once because the code is copied 8 times and there's a bug in the original code. So you want to isolate as much common code as possible, and this sounds like a good tool for it. If you guys know of another awesome tool, please let me know after, and we'll love to try to use it. Another big way we actually make things work is when you have one repo with 600,000 lines of code in it. It's hard to do. So you try to shrink the project scope. When we started out, OpenStack just about 3 years ago had Nova and Swift. Nova is compute, Swift is storage, and the same features today and same functionality is spread out over 6 projects. We have Nova for compute still, Swift still for object storage, Glance for image storage, that was pulled out of Nova, Keystone for user management, once again pulled out of Nova, Cinder for volume management. You want to have an instance, you want to attach a persistent volume to it, Cinder does that for you. Neutron, which used to be Quantum, which is network management. And so we break them all down, we put a REST API between them, which is a contract between projects. You can't change the REST API, we'll test for that. And that means if somebody's optimizing Keystone, they're making it 10 times faster, and we're really grateful for that, but it changes everything inside of it. As somebody working on Glance, Nova, or Cinder, you don't have to know about that. You'll just see everything stays the same from the outside, and the code changes on the inside, and it's, oh wow, everything worked faster now, that's wonderful. And so that's a big way we've helped make things work, is break things down when possible, and use real REST APIs. The good part for REST for us is that it's an easy way to make a contract between projects. So it's easy to test. They're hard to change sometimes, and so that makes them easy to enforce so they don't change. And that's it. Any questions? Yes?
Good.
Oh.
Is it working? Working?
Yeah. I was wondering, do you have any working process when you introduce a new tool that checks for something in the code? Initially, it will result in a lot of failures.
Yeah, so that's been a big challenge for us. There's a few ways we do that. So, for example, the hacking tool for the style guide enforcement, the way that evolved, and this is a common way other things evolve, is you write the tool, or you start running the tool against the code base, and then you start fixing it. You start fixing the problems with it, and then you get to the point where you only have, you have, let's say, 5,000 problems with the code based on this tool. And so you fix, 4,500 of them. You got most of them slowly. And then you have the last few, then you can actually say, you fix the last few and enable the tool for gating. We're currently, for example, getting rid of locals in our in our strings. So one of the problems of using locals for a big project is that, the locals dictionary could just change under you, and it's hard to test, and it just makes things confusing. And we've had a lot of problems in the past with locals, so we're getting rid of them right now. So what we're doing right now is we're fixing all the examples of using locals in a string, percent parentheses variable name s. And we're trying to fix those all. Once we have those mostly fixed, we'll enable gating on that and fix the rest in the same patch.
Did you try with doing something like track the number of warnings and don't let them grow?
Yes. We're doing that for Pylint, actually. So Pylint, when you tried running out of Nova, we had some astronomical number of bugs that it caught, or concerns it found. And so somebody wrote a tool to run it on the previous patch, your patch, it's trunk minus your patch, run Pylint on that, then run it again on yours, and make sure the number doesn't go up. So that's another tool we've been doing, is making sure things don't get worse. And that's, if we can't make them better, at least don't make them worse.
Thank you.
Thank you. That was a very interesting talk. I have a few questions. One is, how do you deal with the process that basically leads up to a patch? So, for example, in Python development, what you usually do is you open a ticket, you just you have some question, or you have a suggestion, then someone adds a patch for it, then you discuss the patch on that ticket. Few people try it, review it, make suggestions, etc., and then finally you merge the patch. And because on your slide you just talked about basically the path from when you already have the patch to how it goes into trunk.
Right. So we use Launchpad for that. Launchpad we use for tracking all our blueprints and all our bugs. So there's two basic ways that'll happen. One is you're a consumer of this. You have a bug. This environment, this thing doesn't work. I don't want to fix it. Somebody else fix it. You file a bug. It'll get triaged, maybe critical, unimportant, won't fix, whatever it is. And either somebody else will fix it, or if you want to fix it yourself, you can go and fix it. So the triaging bugs and isolating which bugs are important and critical and how to fix them, that'll happen commonly on Launchpad. Although sometimes it happens in IRC. If it's, somebody will say, hey, look at this new bug that somebody posted. How do we fix it? They'll talk on IRC how to fix it, and they'll post it. The second part, though, that will happen is somebody posts their first attempt at fixing it. Somebody new comes into the ecosystem. They try to, fix the patch. We'll discuss it on Garrett, actually, what their patch should look like. So we'll say, this is awesome, great, let's merge it. Or maybe it's, well, this is good, but what about this condition? Or what about, could you add some more tests to it to make sure we don't, this doesn't change it again.
What about, I mean, there are often different ways of fixing something, or different ways of implementing something, different strategies. How do you discuss those? On Launchpad as well, or?
It depends. So sometimes it's Launchpad, sometimes that's on the actual, the patch set, so on Garrett itself. That's actually something we need to improve on, which is there's about, the number of, I think, core reviewers is about 100 for about 800 to 900 developers total. So it's a pretty good spread. But not every reviewer, not every core developer per project will look at each patch for that project. So sometimes different people may have different ideas about it. So sometimes it'll get fixed in a way that maybe shouldn't have been fixed that way, and we have to refix it again. So that's something we're actually still struggling with. But generally we use, if you want to get feedback, you go onto IRC or go to the mailing list, or post on the bug itself. I think I should fix it this way. What do you guys think?
Okay, thank you. And the second question is, how do you manage refactoring? Because you often have to touch lots and lots of files for refactoring, and it can be confusing for people working on those particular files.
Yes, painfully, very painfully. There's actually, we're going through some assorted refactoring right now, and it's always happening. I looked at the stats, I think the last release, and there's enough commits to rewrite the code like once or twice. So the code's always changing. For refactoring, we try to keep the code, the lines change per commit to be about under 500 or so, because after that, you try reviewing like a 5,000 line commit, it's just not fun. So you try to keep patches fairly small, but in a refactor, you don't want to have one patch per line. It's just not going to work. And then, so if you git clone the project, you write your code, and you try to push it up, and something was refactored under you, you just mutter to yourself and curse somebody out, and then you rebase and hope for the best. That's been another problem we're trying to work on, which is sometimes a patch may have change a lot of things, and there's a high chance of collision for rebasing, or merging rather. So you may know that if this doesn't get merged in 2 days, we'll have to rebase it and try again. And that's something we're trying to do a better job of prioritizing commits, which ones we should focus more on.
You use branches for preparing and refactoring patch?
Yeah, so we use branches in a bit of a different way. We don't really have the concept of long-running branches. Garrett uses branches in 2 basic ways. You write your code, even if you commit it to master, you type in git review. Garrett will see that you only have one patch different than the remote to push up, so you push that one patch up, and that'll be in a separate branch. So that doesn't get merged in. So Garrett has every patch coming in is its own branch. And if you want to have a bunch of dependent commits, you could have your own branch locally, and you just do git commit, git commit, git commit, git commit. You have 3 patches in one branch. You type in git review. That'll be 3 patches that are dependent on each other.
I was more referring to something that where you say you want to do a refactoring, and everyone knows that it's going to be refactored. So you open up a new branch, and all the patches going into trunk from then on have to be applied to both the branch and the trunk?
We don't do that, no. We don't want to. We only fork we fork stable branches. So we have master as our development branch. You could have your local branch like that. So if you're working on a work in progress, you may have you and a bunch of guys may be working on something on the side and doing something like that. But once it goes to trunk, everything's on master. Thank you.
I was just going to mention that for long-lived branch, we have like stable branch, so we could use like stable branch. And we used that feature once. We don't really use it, but there is support for it in Garrett. But for Keystone, we had a rewrite of Keystone, so we did like a completely separate branch for that thing, and we worked on it, and after we just merged in the master. But usually in OpenStack, we just do everything in master. Break it as well.
You mentioned you're using Pylint. I'm curious to know if you've turned a number of the style checks off in Pylint because it's very strict.
I actually don't know off the top of my head. I would have to check. But we don't actually make sure everything is there's no Pylints. We only make sure that there's no new problems. I don't think we run all of them based on how strict you say it is, because Pylint generally has been pretty good lately. I think my guess is that our other code style checks probably they're overlap a lot with Pylint. For example, Flake8 supports no unused imports. That's been a nice one for us because it turns out when you refactor code a lot and there's hundreds of developers, you get a whole bunch of unused imports, and so Flake8 does a pretty decent job of actually checking for that. So a lot of it ends up in Flake8.
I found Pylint to be quite a lot stricter than Flake8.
Yeah, so I've actually looked at different unused import tools, and things like Pylint and others are better than Flake8, but one step at a time.
Thank you for the talk. You said that Pylint run just on the diff. Mm-hmm. Is it an option of Pylint, or is something that you orchestrate?
No, it's not. Yeah, it's I think a bash script we have.
Sorry?
It's a bash script. So it involves Git, so it's Pylint plus Git.
So
Git checkout head, caret, Pylint, record the output, Git checkout head, Pylint, record the output, do a diff. Something like that.
So it's something that you implemented.
I didn't personally implement it, but something OpenStack implemented. It's not it's just a short-term solution for us. Maybe long-term, but it's a hack for us.
Is it interesting because if you start using Pylint after that, a lot of the code has been written. If you don't do the Pylint on the diff, you should check also the lines that you don't modify.
So it does a good job of actually detecting what the script makes sure that only running on the new code to it. So we haven't seen too many false positives, if any, with the Pylint tool we use. So we've been happy with it.
Okay, so thumbs up. Unfortunately, thank you very much, Joe.
Yep.
Thank you.